Good day. For this session, I am to talk about the determination of osmolality. For the learning objectives at the end of this lesson, you're all expected to define osmolality, determine the effect of ionic compound dissociation on osmotic concentration, and lastly, to compute for the osmolality and osmolal gap values. So let us focus on the main point of this discussion, the osmolality. In our previous discussion in the electrolytes, we have learned that the environment of the human body consists largely of water-based solutions, and a large number of different solutes may be dissolved in these water-based solutions. And also, we learned that the movement of the materials across the cell membrane is heavily influenced by both the differences in the concentrations of these materials, like the electrolytes, across the cell membrane, and of course, the permeability of the lipid bilayer of this cell membrane to these materials. So it is critical that we understand how the concentration of a particular solute is quantified. So in this case, we will talk about how we could get the concentration of the solute by this topic, the osmolality, and as well as how the differences in the concentration of these solutes could influence the passive membrane transport. So first, let's define osmolality. So osmolality is a physical property of solution that is based on the number of particles of the solute relative to the mass of solvent. And it is expressed as millimoles per kilogram of solvent. So millimoles of solute per kilogram of solvent. So that is expressed as weight per weight. And these methods of determination of osmolality are based on the colligative properties. So when we say here colligative properties, that means it is based on the changes in the physical properties of the solutions. So these colligative properties include the freezing point, the vapor pressure, boiling point, and of course the osmotic pressure. And once the solutes are dissolved in a solvent, like for example, if the solutes are dissolved in our blood, which is mainly water of course, these colligative properties will change. So like for example, the freezing point and the vapor pressure will be decreased, whereas the boiling point and the osmotic pressure will be increased. And in the clinical setting, in our work, for example, as medical technologists, this freezing point and vapor pressure are usually measured as a function of osmolality. Now, how do we compute for osmolality? Again, osmolality is the ratio of moles of total solute particles per kilogram of water. So in this case, water is the solvent. And take note that 1 osmol is equal to 1 mole of total solute per kilogram of water. So the calculation of this osmolality can be somewhat more challenging than the calculation of molality, because you have to take note, in osmolality, if we are dealing with a solution that contains only one or single non-dissociating solute, then the osmolality of the solution is equal to the molality of the solution. So again, that is if we are dealing with a solution with one non-dissociating solute. However, if the solution contains multiple solutes, for example, so the number now of the moles of each solute must be calculated independently. Then, the total number of solutes, so the total number of solutes particle will be determined by adding together the number of moles for each individual solute. So that is a bit tedious when we compute for osmolality, because we have to compute for the concentration of each solute particle dissolved in this solvent, in this case, the water. And this osmolality is also measured using osmometers, or estimated using the sum of all the solutes present in the plasma. So this is now the formula. So osmolality is equal to the moles of total solute over the kilogram of solvent. And also, I have mentioned that the normal plasma osmolality is approximately 295. And 275 of which, okay, in the previous discussion, I mentioned this one, that 275 of which is because of sodium and associated ions. Now, let us have the sample problem here. So, calculate the osmolality of solution containing 18 grams of glucose with a molecular weight of 180 grams per mole and 23 grams of glycerol, molecular weight of which is 92 grams per mole, mixed with 500 ml of water. So, in this sample problem, we are dealing with multiple solutes. So, as what I have mentioned, when we are dealing with these kinds of solutions, we need first to get the number of mole of each solute. So in this case, let's have first the glucose. So for example, we have the glucose, which is 18 grams divided by its molecular weight. So this would give us 0.1 mole. For the glycerol, it's 23 divided by 92. So this one, it's 0.25 moles. And again, we need to get the total number of moles of solute. So 0.1 mole of glucose added to 0.25 moles of glycerol. So this would give us 0.35 moles of the total solute. So now for the osmolality, so it's 0.35 divided by 0.5. So take note, this kilogram of solvent must be expressed in liters because 1 liter is equal to 1 kilogram. So 500 ml, that is equivalent to 0.5 liter. So this would give us 35 divided by 5, 0.7 osmol. So that is our osmolality, having the fact that we have multiple solutes. Now let's have the osmolality determination for ionic compounds. So additional considerations must be made for ionic compounds. So number 1, ionic bonds can be broken when an ionic compound is placed in water. So this is because the water molecules have an electrostatic attraction to each of the ion in the ionic compound, and the combined draw of the many water molecules on each ion can now exceed the draw the ions have for each other. And also, the ionic compounds have the tendency to dissociate, or let's say break apart, when dissolved in water. Just like, for example, this one. So we have NaCl, or sodium chloride. So this is one molecule of salt. But when we place this and dissolve it in water, it will separate into 2 moles, one of sodium and one of chloride. And this can have a considerable influence on the osmotic concentration of a solution. So to understand it better, let's have this illustration. So this one shows the effect of ionic compound dissociation on osmotic concentration. So what we have here are 2 solutions. This is on the left and this one on the right. And these solutions are separated by this semi-permeable membrane. And as what we can see here, these 2 solutions have the same molality. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 for this one and also 12 for this one. However, if we take a look at the solutions at the right, we could see that the right side has ionic compound as its solute. So what will happen now is that these ionic compounds will dissociate. So what will happen is that this is still 12. Now this will become 24. So as a result, and applying the principle of osmosis, the water will move from an area of low solute concentration to an area with high solute concentration. So that is what is happening when we are dealing with ionic compounds. Now let's calculate for the osmolality of ionic compounds. So determine the osmolality if 22.2 grams of calcium chloride is dissolved in 3 liters of water. So what you need first to do is you have to determine the number of moles of calcium chloride. And take note, how do we get the molecular weight of calcium chloride? So this one. So we need to have this one, the periodic table of elements. So for the calcium, we have here, calcium it's 40.08. And for the chloride, so it's here, so 35.45. So 35.45. So that 35.45 multiplied by 2, that would give us 70.9. Added with 40.08. So now that would give us 110.98. Or this will become 111 grams per mole. So now that we have the molecular weight of calcium chloride, we can now divide it with the moles of the calcium chloride. So we have now, number 1, determine the number of moles of calcium chloride. So calcium chloride is equal to 22.2 grams divided by its molecular weight, so 111 grams per mole. So this is 0.2 moles. Next one. Number 2, what we need to do is to determine the number of solute particles in a solution that would be formed after dissociation. So after this one has dissociated, we have 3 solute particles, 1 calcium and 2 chloride. So that would mean 0.2 moles multiplied by 3 solutes. So that is 0.6 moles. And lastly, we can now get the osmolality. So that would be 0.6 divided by kilograms of water. So this is 0.2 osmoles. What are the clinical applications of osmolality? So osmolality is ordered to help evaluate the body's water balance or its ability to produce and concentrate urine. Another one is that when we take a look at osmolality, it's kind of giving us a snapshot of the number of solutes present in our specimen, in our blood, in our serum, in our urine, or even in our stool. Next one, it helps investigate hyponatremia. And actually, this serum osmolality is primarily ordered by the physician to investigate hyponatremia or low sodium level in the blood. Next, it detects the presence of toxins like methanol and ethylene glycol. Also, it monitors osmotically active drug therapies such as mannitol. So this mannitol is used to treat cerebral edema, and also we have other osmotically active agents such as the glucose, and we have the glycine. So this glycine is a chemical used in surgical irrigation fluids. Now let us have the formula for calculated osmolality. So why do we need this one? So I mentioned earlier that osmolality can be measured using osmometers. However, osmometers cannot distinguish between effective and ineffective osmoles. That is the reason why we need to have this one, because effective osmolality can only be estimated using this formula. So for the formula, we have 2 sodium here. This is in MEQ per liter added with glucose. So this is in conventional unit. So if you want to convert it to SI unit, just divide it by 18. That would now be in millimoles per liter. Add the BUN. This is also in conventional. So to convert it to SI, we have to divide it by 2.8. And also, if an ethanol is included in the formula, for example, we could just add ethanol here. So for the ethanol, so we have ethanol divided by 3.8. So that would be the formula of calculated osmolality. But if the problem is already in SI unit, so we can directly get it just like this one. So 2 sodium in millimoles per liter added with glucose, which is in millimoles per liter, and also the BUN, which is also in millimoles per liter. So take note, the conversion factor for the conventional and SI unit for the electrolytes is 1. That's why it doesn't change here. So that is the formula for calculated osmolality. Now let us have the formula for osmolar gap or osmotic gap. So osmolar gap is the difference between the measured and calculated osmolality. So this calculation compares the measured osmolality with the measurements of the major solute. So that means the osmotic gap or the osmolar gap is the difference between them, the measured and calculated osmolality. And we have here the formula, the measured osmolality minus the calculated osmolality. And take note of this one, the osmotic gap, which is greater than 10, is already considered as an abnormal result. And this kind of osmotic gap, this abnormal osmotic gap, indicates the presence of osmotically active substances. So we have here methanol, also ethanol. Next, the presence of ketone bodies, and also the acetone, and also we have isopropyl alcohol, and next one, the propylene glycol. So in particular, this propylene glycol is found as a diluent for some intravenous medications such as the drug lorazepam. So lorazepam. And take note of the mnemonics slumped. So these are the conditions causing increase in unmeasured anions, like what I have mentioned earlier, the ethanol, the ketones, and etc. So we have the salicylate intoxication, lactic acidosis, unmeasured ions, methanol, polyethylene glycol, the ethanol, and of course we have this one, diabetic ketoacidosis, because again, as what I have said, glucose is an osmotically active substance. So what are the means of controlling osmolality? So generally, we have two. First, it is thirst sensation. Next one, ADH or vasopressin secretion. And take note, the thirst sensation and ADH secretion are controlled by our hypothalamus. So first, we have this one. The natural response to thirst is to consume more fluids. So that would now result to increase water content in the ECF, and that would now result to a dilute sodium level in the blood. And since sodium is the main determinant of plasma osmolality, we would expect a decrease in plasma osmolality. Next one, for ADH or vasopressin secretion, so again, the ADH is secreted by the posterior pituitary gland, and once it is released by the posterior pituitary gland, it would act or it would stimulate the collecting ducts of our kidney to increase water reabsorption. And also, just like thirst sensation, it would decrease the osmolality. And take note of this one. If we have 1 to 2% increase in osmolality, that would cause a 4-fold increase in ADH secretion or the ADH concentration in the blood. And also, if we have 1 to 2% decrease in osmolality, that would shut off the ADH production. And just an added idea, so the ADH has a half-life of 15 to 20 minutes. Now, what will happen if we have excess water load or what we call as polydipsia? So that condition will decrease the plasma osmolality. So that means the number of solute present in our blood is relatively lower because we have an excess water. So what will happen is that our hypothalamus will not activate thirst sensation and ADH production. So both processes are suppressed. So as a result, water is not reabsorbed. So water will be excreted and a large volume of dilute urine is excreted daily. So around 10 to 20 liters. So this is also seen in diabetes insipidus. And also, you have to take note that impaired renal excretion of water will result to hypoosmolality and of course, low sodium level in the blood. Now, what about if we have water deficit? So this one increases plasma osmolality as opposed to water load. So in this case, the ADH and thirst are not activated by the hypothalamus. And take note of this one. although the ADH contributes mainly by minimizing renal water loss, it is this thirst mechanism that is considered as the major defense against hyperosmolality and hypernatremia. And in this case, we have an example, diabetes insipidus. So this condition would result to excretion of 10 liters of urine per day. And because thirst persists in this condition because of the action of the hypothalamus, the water intake will match the output, so the plasma sodium will remain normal. So that's it for this session. Thank you very much.